So in the last video, I introduced this idea of parameterizing curves and went through a couple different examples to try to show some of the usefulness of it. In this video, I want to get a little bit deeper into the details of how to parameterize curves. And as is often the case when we want a first example in something, we're going to deal with linear equations because they tend to be the simplest type of equations. So maybe first a tiny bit of review. I bet at some point you were able to come up with the equation of a line if you were given 2 points on that line like you see pictured here. Maybe when you think of the equation of a line, you think y equals mx plus b, so you're really just trying to solve for m and b. And sometimes you're lucky enough to just look at the graph and be able to tell what the y-intercept is. Looks like it's 1 in this case, and that gives us the value of b. But sometimes graphs are inexact, so it's not a great idea to use points that aren't specifically labeled when we're looking at graphs. So maybe I should solve for the y-intercept b to make sure that it in fact is 1, and then also figure out what m, the slope, is for this line. There's a few ways to do this, but what I typically like to do is first figure out m. M, the slope, is a measure of the steepness of the line, informally speaking. If you're the formula type, you might think about it as the difference in the y-coordinates divided by the difference in the x-coordinates. So since we're given 2 points, we can arbitrarily call one the first point. So x1 would be equal to -2, and y1 would be equal to +2. And if we're calling this our second point, then x2 would be equal to 4, and y2 would be equal to -1. Taking those 4 values and plugging them into this formula, we get -1 minus 2 in the numerator, so -3, and 4 minus -2, so +6 in the denominator. -3/6 is equal to -1/2. That's the slope of this line. Oh, right, I vaguely remember something about rise over run. So if I want to get from this point to another point on the line, I have to go down 1 unit and to the right 2 units for the -1 divided by the 2 that represents this slope. Yeah, anyways. At this point, we have options in how we can come up with this equation. A more straightforward way would be to plug this value in for m and then plug in either of these 2 points for x and y so that we can solve for b. But what I'm instead going to do, because it'll be useful later in this section, is to use the point-slope form of a line. So y minus y1 equals m times x minus x1, and get directly to this slope-intercept form from here. So if instead of writing m, I write -1/2, because above I solved for m to be equal to -1/2. And instead of x1 and y1, I can plug in -2 and 2, respectively. I get here. And now, since I want this to be in slope-intercept form, all I gotta do is solve this equation for y. So I got y minus 2 on the left-hand side, and on the right, if I take this -1/2 and distribute it through, I'd have -1/2 x, and then -1/2 times the +2 that you see here, because when you're subtracting a negative, you get a positive. So -1/2 times +2 is -1. Now if I add 2 to both sides of the equation, I get y equals -1/2 x plus 1. This is what's referred to as the slope-intercept form of a line, because it gives you both the slope, -1/2, and the y-intercept, +1, as values in the equation. Sure enough, this line appeared to go through the point 0, 1, in other words, have a y-intercept at 1, and we confirm that algebraically by using the 2 points given on the line. And maybe you're like, yeah, but aren't we supposed to be parameterizing these curves? Yeah, now that we have the equation of this line, it's easy enough to parameterize it. One way is just to pick one of the variables, so I'll pick x, and set that equal to t. So if x is equal to t, well then y is now equal to, I can copy what I see written here, except instead of writing x, I'm going to write t, because a minute ago I said x was equal to t. So y is -1/2 t plus 1. By choosing to set x equal to t, and then changing all the x's in my equation into t's, I've managed to parameterize this curve that we had down here. And while we're here, it's worth pointing out that if I was given these equations, this parameterized form of the curve, it'd be easy enough to get it back down into this standard form by just solving one of the equations for t and plugging it into the other equation. In this case, x is already solved for t, so it's really easy to take this equation, y equals -1/2 t plus 1, and change all my t's into x's because, again, it's already solved, and I get -1/2 x plus 1, the same equation that I had down here. The point is, it's easy enough to go back and forth between the standard form of an equation and the parameterized form of an equation. If you're given the equation in its standard form and you want it to be parameterized, if you're lucky enough to have one of the variables already solved for, just take the other variable and set it equal to t. So in this case, I'm going to set x equal to t. It's a kind of trivial way of parameterizing the variable x by just setting it equal to t. And if x is equal to t, it's really easy to parameterize y because y was already solved for in terms of x, which I'm now calling t, so I just copy exactly what I saw here, changing all the x's into t's. Well, it can't possibly be that simple. Well, it's not that simple. It's just that simple when we're dealing with linear equations. But what we'll see in the next video is with more complicated equations, the process of parameterizing is a little bit more challenging. But one step at a time. The other thing we've done so far is gone from our parameterized equation back to the equation in its standard form. And again, in this specific example, that's pretty easy. But generally speaking, what you want to do is solve one of your two equations for the variable t. So because my parameterization of x was so simple here, it's really easy to solve this equation for t. It's already solved for t. But maybe you can imagine some other case where x isn't just equal to t, x is equal to, I don't know, like 3t plus 1 or something. Well, no problem, just solve that equation for t, and then go to your other equation and replace all of the t's in that equation with whatever you solved t to be equal to in terms of your first variable. Linear equations are almost too simple to really understand what you're doing here, but we'll see more examples to really drive the point home. Anyways, with this parameterization, what's going on is that the x-coordinate is just equal to time. So at time 0, my point, a particle if you want to think about it that way, is on this line with an x-coordinate of 0. So right here at the y-intercept. At time 1, it has an x-coordinate of 1. At time 2, it has an x-coordinate of 2, so I'm over here on the x-axis. At time 4, I'm down here at this point with an x-coordinate of 4. And if I wanted to be on this point over here, I'd have to think about time -2, whatever that means. But what if that's not the parameterization you want? What if we want to parameterize the curve so the little particle starts out over here at 4, -1? So at time 0, it's over here, and then at time 3, the little particle's moved over here to -2, too. And to keep things simple for now, we'll assume that the particle moves at a constant speed. This parameterization is not going to work, right? Because this parameterization leaves the point here at time 0, and it kind of heads left to right in my picture because the x-coordinate is just given by the time. So even though this is a parameterization of this linear equation, it's not the parameterization that we're interested in. Well, for this parameterization, I think it kind of helps to keep track of a chart. We have 3 different things changing here, right? We have t's, and then we have x's, and we have y's. And the t points that we're interested in are at time 0 and again at time 3. And at time 0, the point is supposed to be at 4, -1. So its x-coordinate is 4, and its y-coordinate is -1. However, at time 3, the point's supposed to be at -2, 2. So its x-coordinate is -2, and its y-coordinate is +2. What we're going to end up doing is almost the exact same work that we did to come up with this equation in red right here. Except we don't want to express y in terms of x. We want to express x in terms of t and y in terms of t. Sometimes you'll just see x equals, and sometimes they'll even specify that the variable that we want to write x in terms of is this letter t, and the variable we want to write y in terms of is the variable t. How do you do that? Well, let's first worry about the x's. Because the particle's moving at a constant speed, we want a linear relationship between time and our variables x and y. What I'm saying is we want to use the top 2 rows of this table to come up with the equation of a line, but not a line that writes y in terms of x, a line that writes x in terms of t's. So it'll be the same steps we did over here, except the x will be playing the role of the y, and the t will be playing the role of the x. Oh man, that's going to be confusing. Well, it's not too bad. Think about what we did up here first. First, we had to figure out the slope. We just used the letter m for it before, but maybe it makes sense to call it like m of x now. So we're talking about the slope of the linear equation x that we're going to write in terms of our variable t. Well, up here, it was just the difference in the y's divided by the difference in the x's. So it's going to be something very similar down here, except remember, playing the role of the y's up here are the x's, and playing the roles of the x's up here are the t's. So instead of the difference in the y's divided by the difference in the x's, it's going to be the difference in the x's divided by the difference in the t's. So if I call t1 0, then x1 is 4, and t2 is 3, and x2 is -2. Plugging those all into my equation, I get -6 divided by 3, or -2. The slope of the linear equation that I'm going to write down here that represents x in terms of t is -2. Now that I have the slope, I can use the point-slope form to come up with the equation. However, for point-slope form, it won't be y minus y1, it'll be x minus x1, because again, the x's are playing the roles of the y. And then that's equal to m, which I'm denoting m sub x, so I keep straight which slope I'm talking about, times, it used to be x minus x1, but because x isn't my variable down here, t is, it's going to be t minus t1. Plugging in x1, m of x, and t1 gets me here an equation that I can solve for x. Because t minus 0 is just t, I can take the negative 2 times the t and get negative 2t over on the right side of my equation. And if I add 4 to both sides, I get x equals negative 2t plus 4. Note that what I have here is an equation that tells me the value of x in terms of t. What I have is the parameterized value of x in terms of t. I'm just not going to parameterize it in this simple way that had it start at 0. I'm going to parameterize it in this way so that I start at the coordinate that I want to start at, namely 4, negative 1, and I end up 3 seconds later at the point that I want to end up at, negative 2, 2. X of t is just negative 2t plus 4. If you didn't quite follow that, it's totally fine because we're going to do the exact same thing again for y of t. We want to write y as a function of t. So we'll be copying the steps that we did up here, except instead of writing y as a function of x, we want to write y as a function of t. What that means is that my y's down here will be just like my y's up here, but the x's up here will be t's down here. First, I want to figure out the slope. Maybe I'll denote it m with a little y in the subscript, so I keep straight the fact that I'm talking about the slope of the y coordinate as a function of t. Instead of the difference in the y coordinates divided by the difference in the x coordinates, or the difference in the x coordinates divided by the difference in the y coordinates, I'm going to want the difference in the y coordinates, the thing that I'm solving for, divided by the difference in the t coordinates, the variable that I'll end up writing y in terms of. y2 is equal to 2, y1 is equal to negative 1, t2 is equal to 3, and t1 is equal to 0. So I get 3 over 3, or just 1. Now that I know the slope of y in terms of t, I can come up with the equation of y in terms of t by using point slope form. Instead of y minus y1 equals m times x minus x1, I'm going to have y minus y1 equals m sub y times t minus t1, the variable that I want to write y in terms of. Now all I have to do is plug in values. Y minus the value that I had for y1 was negative 1, must be equal to the slope of the y coordinate in terms of t's, in other words just 1, times t minus t1, although t1 was just equal to 0. Y minus negative 1 is the same as y plus 1, and because t minus 0 is t and 1 times t is just t, I get y plus 1 is equal to t. So to solve this equation for y, all I'd have to do is subtract 1 from both sides. What I've managed to do is express the value of y in terms of the variable t. I've parameterized my y coordinate. Y is just equal to t minus 1. This is a second parameterization of this curve given in this standard form. The green parameterization and the blue parameterization both represent the line graphed in red and this equation shown in red. The only difference is the parameterized equations keep track of location at different times. Here I just chose location to be as simple as possible, but in the blue example, my location was specified, so that changed my parameterization. And while you don't need to check your answer, because we learned up here how to go from the parameterized form back down to the standard form, we can check that this parameterization really is of this straight line. Because we want to end up with an equation that's solved for y, it makes life easiest to take the other variable, the letter x, and solve that equation in terms of t. So I have x is equal to negative 2t plus 4. So if I want to solve this equation for t, one option would be to add the 2t over to the left, and then subtract the x over to the right, and then divide both sides of the equation by 2. So I got t is equal to negative x plus 4 divided by 2. I can take this value of t and substitute it into this equation, which expresses y in terms of t. Y is equal to t minus 1. But if I want y to be in terms of x, all I got to do is change this t into this expression, which is in terms of x. So instead of t minus 1, I'll write negative x plus 4 divided by 2 minus 1. Finally, if I simplify this by recognizing that negative x plus 4 over 2 is the same as negative x over 2 plus 4 over 2, and then recognize that negative x over 2 can be rewritten as negative 1/2 x, and 4 over 2 is just 2, and 2 minus 1 is just 1, I get y is equal to negative 1/2 x plus 1, which, sure enough, is the exact same equation that we started this whole mess with up here in red. The point of this video is just to see that if you have an equation in its standard form, you can rewrite it in a parameterized form. But there's lots of different ways that you can parameterize it. Sometimes you don't care about position, in which case just do the easiest way possible. But sometimes you do care about location, in which case the location will be specified, and as long as the particle is moving at a constant speed, coming up with the parameterizations is really just a complicated way of doing something that you've been doing for a long time, coming up with the equation of a line from two different points. You just have to be careful about whether you're talking about x's and y's, or x's and t's, or y's and t's. And then finally, make sure that regardless of the parameterization, you can always backtrack and eliminate your parameterized variable, t in this case, to get back to the original equation in its standard form. That's really the gist of what we're doing in 8.6. The only way it can get harder is if the curve given in red is not a line, if it's a more complicated equation. But we'll do that in the next video.